So, in the previous segment we talked about the qualitative differences between the Eulerian and the Lagrangian approach. Now, in this segment we will quantify them. Okay. That means, in a way we will see how to get that function of displacement, say by answering those two steps query, that who is at x now and what is its displacement. Okay. Now, for that what actually you can do is, see, now x suppose is your location at which you are sitting for the Eulerian data collection, and that is, you can write like this, say minus x naught plus x naught, right. Now, what is the meaning of this is, basically the English sentence which I said, who is sitting at x at time t is like this, means whose displacement is, see, this is the displacement. If I draw like this, suppose this is the origin, this was say x naught has moved to say x, and we are small x is the location which we are sitting here. So, this is asking you, now this x naught plus this is equal to x, which where I am sitting now, right. So, this is what I am trying to solving for, means if I can solve for x naught from here, so then I will get it. So, then yeah. Now, what did I use for this? So, I will say it is nothing but x naught times plus a naught sine omega t minus k x naught, right. So, that is how we took, this is that. Okay. So, you see here, or I can write in a slightly different way, x naught plus say a naught sine k, if I remove ct minus x naught is your x, right. Then so again what you should tell yourself, what this equation tells you is, you are trying to find out from this who is that x naught, because x naught is the name of the person, who is that x naught for whom the position, because this is the displacement and this is its initial value. So, x naught plus this position at time t happens to be x. This equation in English is equivalent to this. The solution of this equation will give you whose displacement is such that the capital X, total position is matching with the location where we are sitting now to take the Eulerian data. Capital X is the Eulerian position, x minus x naught is the displacement, right. Capital X is the position, that is why this is the displacement. Okay. So then what? Yeah. So see here we have ct minus x naught, and here these are x and x naught. So see, the time is in a way universal. So whenever we are asking at this time, we are talking in the Lagrangian also, in the Eulerian also, we are talking about the same time. There is no different time for different views. Okay. Whenever we are saying at a particular time, say 9:30, whether it is Lagrangian or Eulerian, we are talking about 9:30. So this time is same for both the approaches. So to take into account that and to make the things easier, what we can do is, we can simply multiply this equation by -1 and add Ct. So then the equation will become Ct minus x will be equal to Ct minus x naught minus this, okay, a naught sine k Ct minus x naught, right. So in this process what we have done is we have created very similar variables in a way, so that both dependencies, x and t, we are clubbing together as a single variable, say z is equal to z naught minus a naught sine k Ct minus x naught. Oh, sorry. So here also I can do that, no? Z naught. Okay, because time is universal for both Lagrangian and Eulerian. So only difference comes from whether z naught or z is the thing. Now, so our job now is to figure out how z naught can be expressed in terms of z, so that then we are done. Okay, so that means what you can do is, see, let suppose a naught sine k z naught is a function of z naught. Assume that the other function which you will come up with will be function of z. Let that be, say, dz, right. So this same function, displacement function, you are expressing in terms of z. We don't know this d. This function we are actually trying to figure out. This one, this displacement, which is in terms of z naught, that means the original particle's name and universal time, this expressed in current location and universal time z, and we don't know this d, so we are trying to figure this out. Now what you can do is, from this equation you can get z naught is nothing but z plus this is dz, right? Whatever this dz is, we don't know what that is, but from here you can write that, and this one you can substitute here, so that you will get an implicit equation in dz. So dz is nothing but a naught sine k z plus dz. So this equation now has completely removed the dependence on z naught. It is a function only in dz. If you can solve this equation, it's an implicit equation in dz. If you can solve for dz, that is the one which you are actually looking for, right? So this is what you wanted to figure out, what that dz is, which was the displacement and which was plotted there in fact. So that means you just have to and then now you can replace z with ct, so you will get x also as the coordinate. So so the solution of this was plotted there. Now this can be solved by any iterative process, because it's an implicit equation. In some cases, if you have particular functions which can be solved analytically, you can do that, or whatever. So for any function dz, now and then in fact what you can do is, you can write this in more generic way. This I did because we had taken this as our displacement function to start with. If you take this as a general function, some fz, okay, so this as a specific case which I had plotted in the MATLAB, which I showed you, for that I had done, but there is no reason why only this should be taken. When you can choose this function to be anything, say fz. So then what you can do is you can get, you know, your dz in terms of where did I get that? Yeah, your dz will be your f. Now f is that function which for the specific case I took as a sine function, f of z plus k dz. Is it so? Oh, sorry, not this. D. Got it? Now you see, compare this with this. I'll write it there otherwise, okay? In the previous case, I had written dz equal to a naught sine of what was there? K z plus, yeah. K z plus dz. Okay. So because f here is sitting for this function, so that could be any function, it need not be a sinusoidal function. So now what you can do is you can take any reasonable function of your choice and try to solve this equation. You have to solve it iteratively, and this actually is equivalent to finding out or answering both the questions. Who is sitting and what is its displacement?
So that shape that was not a sinusoid.
Yeah, it was not sinusoid, it was this dz. This is the function which was plotted there. Okay. And in fact, the velocity is not the time derivative of this.
Repeat the procedure for.
Yes, or else what you can do is, for example, in this case, your dx by dt was, you know, a omega cosine of omega t minus kx, no? Kx. Okay. Now, or you can say that, okay, I'll write it in this form, maybe k z naught. Now, this z naught you can substitute with this. In place of z naught, you just write k times z plus dz. That will be the velocity.
Here d will represent
The same function which you have got from here, because once you got this, if you add z to that, you are actually getting z naught. So z naught is nothing but z plus dz, and now when you are writing this, this is a known function. By solving this, you have figured this out. So that function you put in here and calculate this, you will get the velocity, the Eulerian velocity. And obviously it will not be the cosine of the normal z naught, means for the x naught thing, because you have converted that from z naught to this function. Okay. And then similarly the acceleration. Now what it means is, this velocity which you will get is the velocity of that particle. Means suppose this, you know, is a velocity at a particular x where you are sitting at a particular time. What is telling you is, this is the velocity of that particle which happens to be at x at t. So it answers both those questions. First figure out who is there and what is its velocity. So this who is there question is solved by solving this dz and its derivative, that run by rise thing will give you this. Okay. So this is how you can quantitatively calculate that and plot things if you wish. Okay, so we will stop here for this segment, and I think today will not be able to do the wave equation derivation. So on next class we will do that. Okay, yeah, see you then.